Hey guys, welcome to this video on natural logs in E. And for this video, I really want to focus on the ln and the exponential function because I want you to understand what is an E and what is an ln in more detail. Right, so to start off our investigation, what is E? So the first thing we must understand is that E is an irrational constant. Many people say it's an irrational constant, but you're not wrong. So E is about 2.71, and it just goes on forever like pi. So it's an irrational constant like pi. And actually, E is actually referencing to the very fundamentals of an exponential growth or exponential decay. So an exponential growth would, for example, be, amount of money you have in your bank account. For example, the money in your bank account would double. For example, maybe not double, but will increase at a rate of, for example, 5% compound interest annually. And that and the money you have will actually increase exponentially. So that would be an exponential growth example. For exponential decay, for example, if we had a hot cup of water, 100-degree cup of boiling water, and we place that into room temperature, we place 100-degree hot boiling water into the room temperature, eventually that temperature is going to drop, exponentially decay, and that's going to cause an exponential decay and until the difference between the temperature and the difference between the temperature of the hot glass of water and the room temperature is very small, and that's when the rate of decrease will decrease. So to begin our understanding, we're going to be looking at a graph of 2 to the power of x. So that's y equals to 2 to the power of x. So this is a very basic and common exponentials that we will come across. It simply states that the y value doubles for each increase in the x value. So this means, for example, if I had $1 in my bank account on day 1, then on day 2 I would have $2. On day 3 I would have $4. On day 5 I would have $8. And on day 6 I would have $16, and etc. It keeps going, doubling and doubling and doubling. So we'll start our understanding with just this y equals to 2 to the power of x. So this y equals to 2 to the power of x, that's still an exponential equation, okay? So looking at this graph here, we have a graph of y equals to 2 to the power of x, and as you can see here, we can obviously see a very large exponential increase. So looking at this graph, you can imagine this is a real life scenario with a person that starts off with $1 in a bank account, and their money doubles with every time period t. Alright, so the rate of change, we can actually look at it. A rate of change is defined as the gradient. So this gradient we can look at between a rise and a run between two x values, or in this case, two t values. So for example, if we're looking from individual days, so for example, from day 1 to day 2, day 2 to day 3, so 1 day intervals. So if we're looking specifically at day 2 to day 3, on day 2, I have 2 to the power of $2, which is, I have $4. On day 3, that increases to $8. The gradient would be the rise over run. I gain $4 over 1 day, which means that now that gradient is 4. However, if we're looking at day 3 to day 4, on day 3 I have $8, but on day 4 I have $16. This increases from 8 to 16, that's an increase of $8. That is still over one time period, so this gradient actually increases to just 8. So gradient is now 8. So in terms of, if we're looking at this pattern, if you notice this pattern very clearly, we see that if I have $2 at the start, then I'm going to gain another $2 in the next day. If I have $16 on one day, I'm going to gain another $16. If I have $1,028 on one day, so I'm going to gain another $1,026 on the next day. So as you can see here, it seems that the gradient of the graph at the point is equal to the amount of money I have to start on that day. So that's the money I have to start on that day. So for example, if I started with $4, then after one time period, I would gain another $4, and I would have $8. So that seems to be the pattern that we're seeing here. It seems to be very prominent in our calculations here. So let's not stop there. Let's actually verify our understanding by using a graph. So not graph, this table. This table shows us the intervals of days. So this is a 1 day interval, day 0 to day 1, day 1 to day 2. And this is the gradient between the intervals. So as you can see here, just for a few examples, we have on day 0, I have $1. On day 1, this doubles to $2. The rate of change, or the gradient between these 2 points, I gain $1 over 1 day. The gradient is just 1. So what about day 1 to day 2? So day 1, I have $2. On day 2, I have $4. That increases by $2 over 1 day. So now our gradient is 2. From day 2 to day 3, on day 2, I have $4, and on day 3, I have $8. Because of this, our gradient is actually 8 minus 4 over 1, which is 4. So it seems to be doubling between intervals. And if you notice this graph, it seems to be very similar to the one we just had, the y equals to 2 to the power of x. The gradient between intervals is doubling for each increase in the day. That at 1 increases to 2, doubles and doubles and doubles. So you're saying, oh, this is 2 to the power of x. So because this right hand side represents the gradient between intervals, then this right hand side, this is 2 to the power of x. So that must mean that the gradient function of 2 to the power of x must still be 2 to the power of x, right? It seems very intuitive. It seems very obvious. It's sitting right here in front of us, right? 1, 2, 4, 8. It's increasing. It's doubling each day. It has to be 2 to the power of x, right? Well, that's where we're not actually quite right, because it might be tempting to say that the gradient function of 2 to the power of x is itself, as shown by the evidence of this table in our analysis of its evidence that we have. However, that's actually incorrect. Alright, so how about we try something else, okay? So how about instead of using 1-day intervals, we'll try to use 2-day intervals. So instead of going from day 0 to day 1, we're going to go from day 0 to day 2, day 2 to day 4, day 4 to day 6. I wonder if it's still going to be 2 to the power of x. According to our previous graph, it still should be, right? It doesn't make any sense for that 2 to the power of x to change, right? Let's see. Let's see the values. So we'll use 2-day intervals and we'll investigate the gradient. On day 0, I have $1. On day 2, I have 2 to the power of 2, which is $4. I increased by $3 over a period of 2 days. 3 over 2 is 1.5. On day 2, I have $4. On day 4, I have $16. Oh, sorry, on day 2, I have $16. 16 minus 4, that's 12. 12 over 2 days, so I have $6. So the gradient is 6 per day. Likewise, as you can see here, this is the evidence of the graph. We have our gradient between intervals is increasing by 4 now. But hold on just a second, didn't we just say the gradient between intervals was doubling each day? Why is it now quadrupling each day? So now you can see this graph seems to be more like 4 to the power of x. It seems to be quadrupling each day. That seems very weird, considering that we just said that it seemed to be 2 to the power of x. So as you can see here, we already have a contradiction between what we just found. So that means that our gradient function can't possibly equal 2 to the power of x. So this is the evidence here. So how can it be 2 to the power of x when it's right here? It's 4 to the power of x. Alright, so now we're going to be looking into what's actually happening right here. So what's going on here? Why are we wrong? To understand, according to first principle differentiation by first principles, a gradient function finds the gradient at an instantaneous point. So for example, if you have a function, some function relating two variables, whether that's y or x, d or t, it doesn't matter, relating two different variables, the gradient function, that derivative, that refers to a gradient at an instantaneous point. So whenever in level 2, right, in level 2 calculus in differentiation, a question might ask you to find what is the gradient at x equals to 2, for example. That is asking you what is the instantaneous gradient at that x equals to 2 point. What we were just looking at those two tables, isn't the instantaneous gradient at that point. The table that we were just looking at, that's the gradient between two huge intervals. So the intervals 1 day and the 2 days, we're seeing that big intervals. That is the gradient we're finding. They're not the same thing. So in order to get the true idea of our gradient value, we must find a point very close to our original point. For example, we shouldn't be looking at how the function behaves over 1 or 2 time periods. We should be looking at how the function behaves from very small values. So maybe like 1 over 100th of a time period. Because the smaller the time period, so the smaller the change and the change in the time value, the more accurate it is, because it is a smaller distance away from our original change in time. Because we're trying to find the instantaneous one. So that's realistically no change in t. That's the gradient when there's no change in t. However, that's not really realistically to calculate possible. So if we use a very, very small dt, like 0.00001, we can still get a very, very rough idea of what our gradient function is going to be looking like. Alright, so this is a challenge for everyone that's out there. So I want you to come up with an equation that represents the derivative of 2 to the power of x in terms of a change in t and 2 to the power of t. So give that a try. Okay, it might be a bit challenging, but I encourage everyone to pause the video now and give this question a try. Alright, so what I have here is actually dd over dt that equals to 2 to the power of t plus dt minus 2 to the power of t over dt as dt is approaching 0. So what the numerator here represents is the change in y. So our gradient is, again, the definition of our gradient itself still hasn't changed. It's rise over run. In the numerator, we have our rise. Our rise is the change, so our 2 to the power of d plus dt. So the 2 to the power of t is the point we wish to investigate. So that's the point we want to investigate. dt is a very, very small change in our t. And the difference between 2 to the power of d plus dt and 2 to the power of t, that very small difference, that's going to be our rise. our run will simply just be our change in dt, that very small dt change. So that's our rise over run. And we wish to find what this value is as dt approaches 0, because we want to be dt to be as small as possible, a very, very small change in t. Alright, so in this case, dd is change in money over change in time. dt is change in time, t is just time. So lim, lim, that's just the limit. So that's just saying, what is the value of this equation while a variable approaches to some value. So this equation tells us that the gradient is rise over run and the difference in money d from point t and point t plus dt, where dt is any change in time. We want to find the value of this when dt is approaching 0, so as small as possible, in order to find a gradient at point t. Right, so this, we're going to be simplifying, reducing our equation a little bit. So thanks to the rules of indices, we can reduce our equation. So dd over dt, so for example, if we have indices, right, we have 2 to the power of 2, for example, 2 to the power of 2, if we multiply, 2 to the power of 2 multiplied by 2 to the power of 3, that is equal to 2 to the power of 2 plus 2 to the power of 2, 2 to the power of 2 plus 3, right? In the same case, we can split. Okay, so in the previous example, we were joining the indices. But in this case, we'll also split the indices in the exact same way. So t 2 to the power of t plus dt can be split into 2 to the power of t multiplied by 2 to the power of dt. And the negative 2 to the power of t stays there. So now as you can see, we have 2 to the power of t as a separate variable. As now we can factor it out. We can take it as a common factor. If we take out 2 to the power of t as a common factor, then we'll get 2 to the power of t times 2 to the power of dt minus 1 over dt. So this is very interesting. The reason it's very interesting is, as you can see here, this is 2 to the power of t multiplied by something. We won't worry about what that something is right now, but it's 2 to the power of t multiplied by something. So as you can see here, our gradient function is actually proportional to the amount of to the function itself. So the 2 to the power of t, the derivative of 2 to the power of t is proportional to 2 to the power of t. And if you think about it, that actually makes sense. For example, if we have money in a bank account, let's say this compound interest annually on that money. If we have $5 in our bank account and that gets a compound annual interest, we're going to see very small increases yearly because it's a very small value to begin with. And taking a percentage of 5 is going to generate very, very small values. Let's say we don't have $5. Let's say we have $5 million. If we have $5 million in our bank account and we get compound interest annually on that $5 million, then we're going to be seeing a rapid increase in our money, much more faster than that $5 we were having before. That's because the rate of change is actually proportional to how much money we have in the bank account to begin with. It's actually proportional to each other. That's why. So as you see here, our gradient function is proportional to the amount of money we have in our bank account to begin with. Let's investigate what happens to dt as it approaches 0. To get an idea of our gradient function, let's substitute some very, very small values for dt. As 2 to the power of t doesn't contain dt, we will ignore it for now. So because 2 to the power of t is independent of dt, we'll just cast it aside for now. It's not that it doesn't matter, it does. It's a very important part of the equation. But for the sake of calculating what is that constant there, we're going to just cast it aside for now. So we have a little bit of a table here, very, very, very useful table. So this shows us our value of dt and the value of 2 to the power of dt minus 1 over dt. So that's our weird constant there. If we put in 0.001, we'll get 0.69317 as the value of 2 to the power of dt minus 1 over dt. I use values that are 10 times smaller for each value of dt. So value of dt is getting smaller by a factor of 10. So as you can see here, our value of 2 to the power of dt minus 1 over dt is approaching some constant. This is a very weird constant, 0.693146. That seems pretty strange. Doesn't seem to be any pattern or any logic in this constant, but we'll investigate. What happens? What about if we use 3 to the power of t? What about 7 to the power of t? What about 5 to the power of t? What happens to that constant if we have different bases? Let's investigate. So here we have another table showing different bases. So instead of having 2 to the power of t, we might have 3 to the power of t, 4 to the power of t, 5 to the power of t, 6 to the power of t, and 7 to the power of t. So as you can see here, the value of the constant here is actually increasing. So 1.09861 goes to 1.38629. It just keeps increasing. So as you can see here, as we increase the base, that value of the constant also increases. So this constant is not the same for all exponentials. It's obviously different for each exponential. So as the base increases, so does that constant. Is there a base where that constant is 1? Is there a value for, so now we need to ask our question. This is the big golden question here. So is there a base where that constant is 1? So that constant, 2 to the power of dt minus 1 over dt. Is there a possible way to make that equal to 1? Well, there is. You probably guessed it already. It's e. So e is approximately 2.7182818, and as I mentioned at the start of the video, that's actually equal to, that's actually not equal to, that's actually an irrational number, which means that it continues indefinitely, it continues forever. Like pi has infinite digits, it goes on forever. Just like e, it also has infinite digits, it goes on forever. So that's our definition of e, actually. That's what e is. So and that's the definition of e, a function where the constant is 1. So if that constant is 1, so in the case when we had 2 to the power of t, we had our derivative is equal to 2 to the power of t times a constant. If that constant is just 1, then if it's e to the power of x, then the differentiation is still going to be e to the power of x, because e to the power of x times of 1, that's still e to the power of x. So that's the magic of e. The derivative is the same. E to the power of derivative of e to the power of x, that's still e to the power of x. Alright, what about ln of x? The function ln of x is a log base e. In simple terms, it asks us the question e to the power of what is x. So in level 2 differentiation, we might have come across log base 10 very commonly. So instead of having a log base 10, ln is it's basically saying log base e. So you might see, oh, an ln, that might look scary, but ln is just simply log base e. It's not anything more than that. It's just ln is just some fancy term they decide to use, but in reality, it's just log base e, okay? And it asks us the question e to the power of what is x. So if we have ln of e is telling us what e to the power of what is e. So in this case, e to the power of 1 equals to e, so ln of e has to be 1. Similarly, if we have ln of 2, that's basically asking us e to the power of what equals to 2. That's just asking us the x value for what is that power of e is equal to that x value. Right, coming back to our 2 to the power of x, what exactly is that constant? So at that 0.693, what is that constant? Okay, we need to understand in terms of that constant. We can't just think of it as some number, because it's not just some number. It's something very important, and I'll show you. So y equals to 2 to the power of x, it can be written as y equals to e ln of 2 times of x. Alright, I haven't actually changed the question here, because as we said previously, ln of x is defined as what e to the power of what equals to x. So in this case, if we have e to the power of ln to x, the e and the ln of x will cancel out, and that'll give us 2. So I didn't actually change the question, I just wrote the 2 in a different form. So I wrote the 2 as e ln of 2x. In this case, e to the power of ln of 2, that's still just 2, because the e and the ln will cancel out. In this case, we can now use the chain rule to differentiate this equation. Because if we differentiate this equation, the derivative of the power is ln of 2. If we bring that to the coefficient, we'll get ln of 2 times of e to the power of ln of 2 times of x. We just established that e to the power of ln of 2 is just 2. So this becomes ln of 2 times of 2 to the power of x. And there we go. That's our magical constant. Our magical constant is actually just ln of 2 in this case. So, correspondingly, if we use 3 to the power of x, 4 to the power of x, that would just be the ln to the base of that power. So if we have, for example, if we have 3 to the power of x, the constant would be ln of 3. If we have 1000 to the power of x, the constant would be ln of 1000. So that's the magic. That's the beauty of exponentials. You have that constant is just ln of that base. So the constant is really just ln of x, and x is that base. So that's the magic of ln of x. So we're going to look at some differentiation exponentials. I will be covering what you really need to know for level 3. As studied above, we know that the derivative of e to the power of x is e to the power of x. We can differentiate all the exponentials using the chain rule. For example, if we have y equals to e to the power of 3x, we can actually differentiate that. So the derivative of 3x is 3, and if we multiply 3 by e to the power of 3x, we will get 3 times of e to the power of 3x. And that will be our derivative. Derivative of 3x is 3, so 3 times of e to the power of 3x, that is 3e to the power of 3x. So we put this into a bit more basic terms. The derivative of the function is the function, so the function y multiplied by the derivative of the power of the e. So if the derivative of the power in this case is 3, and the function is e to the power 3x, so it becomes 3 times of e to the power 3x. That's our derivative. And that's how you would differentiate an exponential. So you can really differentiate these exponentials using this chain rule. Let's get a few practice questions done. And for each of these practice questions, I want you to pause the video and I want you to give it a go yourself and then keep watching the video for the answer. So you have y equals to e to the power of 2x plus 2. Alright, so the answer to this question is dy over dx equals to 2e to the power of 2x plus 2. The reason for this is because the derivative of the power 2x plus 2, that's just 2. So it becomes 2 times of e to the power of 2x plus 2. So the 2 gets multiplied, the coefficient, so the power is, the derivative of the power is 2, and the 2 gets moved to the coefficient, so it becomes 2e to the power of 2x plus 2. Question 2, y equals to e to the power of negative x squared plus 5x minus 2. The derivative of this function will be dy over dx equals to negative 2x plus 5 times of e to the power of negative x squared plus 5x minus 2. In this case, the derivative of the power is negative 2x plus 5, and we're going to move that negative 2x plus 5 to the coefficient, and we're going to multiply that by our function. So in this case, we have negative 2x plus 5, e to the power of negative x squared plus 5x minus 2. So question 3, y equals to 3 e to the power of negative x plus 4. So in this case, we will have dy over dx equals to negative 3 e to the power of negative x plus 4. The derivative of negative x plus 4, that's negative 1. So we'll simply multiply the 3 at the front by the negative 1. 3 times negative 1 is negative 3. So it becomes negative 3 e to the power of negative x plus 4. So that's our dy over dx. Question number 4, y equals to negative 4x e to the power of x squared plus 5. So in this case, I actually made a mistake when I was making this video. I forgot to use the product rule in this case. We have to use the product rule with the chain rule because we have two functions multiplied together. We need to use the product rule to differentiate. So in this case, we have negative 8x squared e to the power of x squared plus 5. So the derivative of x squared plus 5 is 2x. So negative 4x times 2x, that's negative 8x squared. However, we still need to incorporate the negative 4, the derivative of negative 4x. The derivative of negative 4x is negative 4. So we need to add on minus 4 e to the power of x squared plus 5 because we need to differentiate negative 4x as well in order to use our product rule correctly. So that's just a little bit of an error I made there, so I apologize for that error. So I hope we have clarified. The actual answer is negative 8x squared e to the power of x squared plus 5 minus 4 e to the power of x squared plus 5. Alright, so question 5, we have y equals to e to the power of ln of x. So as we were stating before, ln is basically just saying e to the power of what is x. So in this case, our e and our ln will just cancel out. So this question actually just get reduced to y equals to x. This is y equals to x. Don't let the e and the ln fool you. This is just y equals to x. If we differentiate y equals to x, we'll get dy over dx. That's just 1. So nice and easy there. So now we're going to be looking at the derivative of ln of x, the natural log of x, so log base e of x. So the derivative of ln of x is 1 over x. So now we want to prove that. So for all the people who are willing to have a challenge, I want you to pause the video now, and I want you to try to prove that the derivative of ln of x is 1 over x. Just to give you a hint, guys, you need to use implicit differentiation in order to get your answer. So you need to use implicit differentiation. So that's my hint. And pause the video now and try this for yourself. Try to prove that the derivative of ln of x is 1 over x. Alright, I hope you've just proved that the ln of x is 1 over x. So what I got here, so we need to differentiate implicitly. So we have y equals to ln of x. Right, so people get really confused. Like I've seen lots of people get confused about ln of x. How am I supposed to rearrange this equation? So people keep looking at this as ln of x, but if you look at it as log base e of x, that makes it a lot easier. So I'll take you guys back to level 2. So in level 2 we had for example a question might ask you log base 2. So that 2 will be written in a very small subscript. So it'll be log, and then a small 2 at the bottom, and then a very big number next to the log, for example, 1024, and that equals to x. So in that case, you could have rearranged the equation 2 to the power of x equals to 1024, and from there you could have solved that x equals to 10. It's the exact same thing here. Ln of x is just log base e of x. So in this case, it would just be log, and then the e will be in very small subscript, and then the x would be the very big number next to the log. Now if we move the log base e of x to the other side, we'll get e to the power of y equals to x. So that's how we rearrange this equation. So e to the power of y equals to x. Now we differentiate implicitly. So e to the power of y times of dy over dx equals to 1. But we know we have to apply the chain rule for differentiating e to the power of y. This is because we're differentiating the function with respect to x, not with respect to y. So when we differentiate e to the power of y, we actually have a composite function, so we need to use the chain rule. So the differentiation of e to the power of y, that's still e to the power of y. We need to multiply by dy over dx, and that equals to 1. Alright, however, we know that e to the power of y equals to e to the power of ln of x. That's because y equals to ln of x. So as we in the previous slide, if you remember, there was a question number 5, that was e to the power of ln of x, okay? We know that e and the ln will just cancel out, so we'll just get e to the power of y equals to x. So now we have x times of dy over dx equals to 1. If we move the x to the other side, we'll get that dy over dx equals to 1 over x. Alright, some practice questions here, okay, for ln of x. So we have first question, y equals to ln of 2x. So I want you to pause the video and try this question for yourself. Alright, so for this question, we need to be using the chain rule, okay? So in this case, dy over dx, so the derivative of 2x is 2. And so 2 multiplied by the derivative of ln of 2x. The derivative of ln of 2x is just 1 over 2x. So 2 times of 2 times of 1 over 2x, that's 2 over 2x. And the 2 and the 2 cancel out, so we get 1 over x. It's a good thing to know that ln of some number times of x, that's always going to be, derivative of that is always going to be 1 over x. That's because the coefficients will cancel each other out, and you get 1 over x. So even ln of 1000x, the derivative of ln 1000x, that's 1 over x as well. Question 2. Y equals to 2 ln of x squared plus 4x minus 8. So I want you to try this question. Alright, so dy over dx, that equals to the derivative of the inner function, which is x squared plus 4x minus 8. The derivative of that is 2x plus 4, and we'll multiply by the 2 on the outside of the ln. And we need to multiply that by the derivative of ln. The derivative of ln is just 1 over everything inside the ln. So now we have 2 times of 2x plus 4 over x squared plus 4x minus 8. And we'll get 4x plus 8 over x squared plus 4x minus 8. That is our final answer. Question 3. Y equals to 3 ln of x squared minus x plus 4 over 3x minus 2. So a slightly harder question now. I want you to try this for yourself. Alright, so what we have here is an unsimplified version. So right now we need to find the derivative of the inner function, which is everything inside the ln function. We need to find the derivative. In order to find the derivative of this function, we need to use the quotient rule. So the quotient rule states that we need to have the derivative of the numerator multiplied by the denominator minus the derivative of the denominator multiplied by the numerator, and everything on top is divided by the denominator squared. So in this case, we will have 3 times of 2x minus 1 times 3x minus 3 times of x squared minus x plus 4 all over 3x whole thing squared, which is 9x squared. And we need to multiply by the 3 on the outside, because we have the 3 on the outside of the ln. We need to multiply that derivative by 3. So that's the 3 on the outside. Okay, so one thing people forget now is we need to divide by, we need to multiply by the derivative of ln. The derivative of ln is just 1 over everything inside the ln function. So now we need to multiply by 1 over everything inside the ln, which is meaning it's going to be dividing by x squared minus x plus 4 over 3x minus 2. I didn't simplify this equation, but if you wanted to simplify this equation, you can simplify the fractions by multiplying by 1 over the reciprocal. And once you multiply by 1 over the reciprocals, you can you can actually expand these brackets inside the numerator, and you can cancel out some of the x terms. Once you cancel out the x terms and you have multiplied by the reciprocal, then you'll get your final fully simplified equation. I didn't actually simplify this equation. Apologize if that's I apologize if that's really inconvenient, but I just left my answer as an unsimplified form. So for question 4, y equals to 3x ln of e to the power of x plus 6x. So in this case, we need to use the product rule on top of the chain rule. The reason we're using the product rule here is because we have 3x multiplied by, so we have a function of x multiplied by another function of x. Because we have two functions of x multiplied together, we need to use product rule, and to differentiate ln, we need to use chain rule. So in this case, we'll start with the derivative of 3x. The derivative of 3x is just 3. So 3 multiplied by ln of e to the power of x plus 6x. So to explain the product rule real quick, for those who don't know, the product rule states that if I have a function f and a function g, product rule is the derivative of f multiplied by g plus of the derivative of g multiplied by f. So that's the definition of the product rule. You can find that on your level 3 formula sheet. So we have 3 times of ln of e to the power of x plus 6x. And now we need to do 3x multiplied by the derivative of ln of e to the power of x plus 6x. In this case, the derivative of the inner function e to the power of x plus 6x, that is e to the power of x plus 6, because the derivative of e to the power of x, that's still e to the power of x. And that's multiplied by the 3x on the outside. So 3x times of e to the power of x plus 6, that becomes 3x e to the power of x plus 18x. And that's divided by the derivative of ln, which is 1 over everything inside the ln, which is 1 over e to the power of x plus 6x. So we're dividing 3x e to the power of x plus 18x over e to the power of x plus 6x. And that is our final answer for dy over dx. And so now I have some practice questions, some similar to NCAA questions, I guess. These questions, I've made these questions. So the population of bumblebees near a park can be modeled by the function t in days, and t is between 360 and 0. So this is a pretty tough equation. So we have p equals to 5e to the power of negative 4 over t plus 4t plus 2 over t squared minus 3t squared ln of 4 over t plus 6 plus 180. Alright, so find the rate of change of the population after 2 days. So I want you to pause the video now and try this question for yourself. Alright, so the first thing you have to do here is, obviously, if you want to find a rate of change, you need to find the derivative of the function. Alright, so in this case, in order to find the derivative of the first half of the function, the exponential part, we need to find the derivative of the power of the exponential. So the derivative of negative 4 over t plus 4t plus 2 over t squared, and we need to multiply that by 5 because when we have an exponential, we're multiplying the coefficient by the derivative of the power. So the derivative of the power multiplied by 5, and then we need to keep e to the power of negative 4 over t plus 4t plus 2 over t squared. We need to keep that the same. And we need to, now we differentiate the second half of the equation, which is 3t squared ln of 4 over t plus 6 plus 180. So in this case, we need to use the chain on top of the product rule and the chain rule together. So in this case, we need to find the derivative of 3t squared, which is 6t, multiplied by ln of 4 over t plus 6. And then we need to find 3t squared multiplied by the derivative of ln of 4 over t plus 6. The derivative of 4 over t plus 6, we can find that using the quotient rule. So the quotient rule states that the derivative of 4 over t plus 6, that is negative 4 over t plus 6 squared. And that is multiplied by the 3t squared on the outside, the negative 3t squared on the outside. And don't forget to multiply, don't forget to multiply by the derivative of ln, which is 1 over everything inside the ln. So we need to multiply by 1 over 4 over t plus 6. So it should be shown by this equation. Right, so right now it looks a bit messy, so let's simplify this equation a little bit more. If we simplify this, okay, we have 4t squared minus 2t times 4t plus 2 in the brackets here. If we expand the brackets, we'll get negative 8t squared. So 4t squared minus 8t squared, that gives us negative 4t squared. If we have negative 2t times of 2, that gives us negative 4t. As you can see here, t is a common factor, so we can factor out a t and cancel with one of the t's in the t to the power 4. That gives us t to the power 3 now. If we multiply everything by 5, so the 5 on the outside, if we distribute the 5 inside the brackets, we'll get 20 over t squared plus 5 times of negative 4t minus 4 over t cubed, and the e and the power stays the same, minus 6t ln of 4 to the power of 4 over t plus 6. We'll keep that the same. And if we simplify this everything on the right hand side here, the negative 3t squared and the negative, they cancel out, it becomes a positive. So that becomes positive 12t squared, so 3t squared times 4, that's 12t squared, multiplied by the reciprocal of 4 over t plus 6. So if you divide by a fraction, it's the same as multiplying by its reciprocal. So technically, if you divide by 4 over t plus 6, you're multiplying by t plus 6 over 4. So once you multiply by t plus 6 over 4, you'll notice that one of the t plus 6 at the top will cancel with one of the t plus 6s at the bottom. And that actually simplifies your final answer to 12t squared over 4 bracket t plus 6. And now we can find the rate of change after 2 days by substituting t equals to 2. As we can see here, if we substitute t equals to 2, we'll get that the rate of change of the population after 2 days is 5.69. And that will be your final answer for this question. Right, so more practice. So a person buys stock in Air New Zealand, and however, after the COVID-19 pandemic struck, the person's stock can be modeled by d equals to negative 2t, e to the power of negative t squared plus 5t plus 0.5 plus 3000. The question is, when t is the time in years after travel restrictions took place, calculate the stock value after 18 months. So pause the video now and try this question for yourself. Right, so in this case, we just need to we just need to substitute t equals to 1.5 into the equation. The reason we're substituting 1.5 and not 18 is because t is defined as the time in years after travel restrictions took place, not months. So 18 months, 12 months in a year. So 18 months equals to 1.5 years. So we're going to be substituting 1.5, not 18. If we substitute 1.5 into our equation, we'll get negative 3e to the power of 5.75 plus of 3000, and that gives us a stock value of 2057.43. That's your answer for this question. Question B, what is the minimum stock price that it falls to? So once again, pause the video and try this question for yourself. Alright, so what I have here is for a minimum, dd over dt has to be equal to 0 because that turning point, the gradient is a 0. Hope we're already familiar from this from level 2. So if we differentiate our equation, we need to use the chain rule on top of the product rule, and the product rule, we need to use them in conjunction. So the derivative of negative 2t, that's just negative 2. So we have negative 2e to the power of negative t squared plus 5t plus 2. And we need to define the derivative of the exponential. The derivative of the exponential, that's the derivative of the power is negative 2t plus 5. So we're going to be taking that to the coefficient, multiplying 2t by negative 2t plus 5. So we'll get negative 2 and, we'll get this equation here. Right, so we need to solve this equation for dd over dt equals to 0. However, we know that e to the power of x can't be 0. The reason that e to the power of x can't be 0 is because imagine something to the power of something else. Let's forget about e. Let's say it's 2. Okay, let's go back to very basics here. Let's say we have 2 to the power of x. No matter what value of x we put for this function, let's say x is equal to negative 1 million. So 2 to the power of negative 1 million, that is going to be a very small number, but it's never going to be negative and it's never going to be 0. So you have to remember that. So 2 to the power of x, it approaches to 0, but it never actually becomes 0. So if we had so it's basically just getting really, really close to 0. Eventually it's going to be so close to 0, but it's never going to be 0 because there's no actual real number. There's no real number that can actually satisfy that 2 to the power of x equals 0. There's no such thing. Okay, so guys, I want you to get your calculator out, and if you try pressing in ln of 0 and see what you get. So basically, as we said, ln is basically defined as e to the power of what equals to x, right? So it's basically saying e to the power of x equals to 0, right? So put ln of 0 into your equation, into your calculator. You should find that you get a non-real error or some mathematical error, and that's correct because there's no such value of x that can give you e to the power of x equals 0. It just doesn't exist. So we know that e to the power of x can't be 0, which means that e to the power of negative t squared plus 5t plus 2 can't be equal to 0 either. So because it's a common factor, let's just get rid of it, okay? It's not doing any good for us, so let's just get rid of it, okay? If we factor e to the power of negative t squared plus 5t plus 2 and factor it out, we'll get negative 2 plus, if we expand the brackets, don't forget to expand the brackets, we'll get negative 2 plus 4t squared minus 10t. At this stage, you can just substitute into a calculator, so a equals to 2, b equals to negative 10, c equals to negative 2, and solve for your t. So you should get t equals to 2.686 or t equals to negative 0.186. Because we know that t cannot be negative, it's strictly positive, we're going to be ignoring t equals to negative 0.186, and we're going to be using t equals to 2.686. So if you substitute if you substitute d equals to if you substitute t equals to 2.686 into your equation, you should get that our stock value comes out to be negative 1,432. When you're doing this, be very careful that you're putting brackets around whenever it's necessary. If you don't put brackets around what is necessary, then you won't get the correct answer. You could get something that's way off the correct answer, and that's very dangerous. So be careful. Be careful to put your brackets around the right place, and don't forget to put brackets when it's necessary. The minimum stock price was negative $1,432. So Air New Zealand was probably bankrupt at this point. You don't have to write that in your answer. It's just a joke, okay? It's just a joke, guys, okay? Alright, so question C. When is the stock price decreasing? So when is the gradient below the x-axis? When is the gradient negative? So I want to give you some more time to find the answer to this question. Alright, so what I've got here is that the stock price decreases when the gradient function is below the x-axis. So when the gradient function is negative, if the gradient function is negative, then it must be decreasing because the gradient is less than 0, rise over run is less than 0, which means that it's decreasing over time. Coming back to our simplified equation, so our quadratic here, when we solve for t, so this represents a positive parabola. So we actually have this parabola right here. A positive parabola is a happy face. Remember, positive happy, negative sad. Okay, this is like a happy face, so this is a positive parabola. And if you draw a positive parabola and the x-intercept, you'll see that it's below the x-axis when it's between the two intercepts. So when it's between the two intercepts, the gradient is less than 0, and when it's between the two intercepts, it is decreasing. So we can conclude that the parabola is below the x-axis when it's between the two intercepts that we found. But we know that t is strictly greater than 0, which means that t is actually between 0 and 2.686. And it's really important that you link this final step into your final answer, because we're taking this into a real life situation. This is not mathematically, it's decreasing between these two intercepts, but technically Air New Zealand didn't really have a negative time, so we can't really say that it's negative. So therefore, we're going to say it's strictly positive. So that's our real life boundaries there. Right, so one more question here. So when I say one more question, I actually mean 3 more questions, but yeah. During the COVID-19 pandemic, the number of cases in New Zealand confirmed on a daily basis can be modeled by cases equals to 1.1243 e to the power of 0.3974 t. So that's an exponential, okay? So t is the time in days, and this is valid for t is between 0 and 11. So it's important to point out that this equation is only valid for this amount of time, because in the real life situation, the number of cases won't increase forever. Eventually, it's going to stop, okay? So eventually, the number of cases is going to level off, and eventually, it's going to start decreasing, okay? So in a real life situation, there's boundaries on when the equation is valid, and the boundary is between t is 11 and t is 0. Alright, so Prime Minister Jacinda Ardern enforced a 4-week lockdown. Cases after 11 days can be modeled by this equation, so this quadratic equation. C equals to 0.636 t squared minus square root of 392.92572 t plus 270.61. Sorry. As a quick disclaimer, I actually used this, got these equations from Excel. I just used the scatter graph function, and I tried to get some approximate function. I got some ideas. I had to change some of the Excel functions because they didn't really make sense, but I eventually got to these functions. They make some sense, and they fit with the situation pretty well. So these are the 2 equations. So this second equation is only true for t is between 11 and 27.5. So between 27 and 27.5 days and 11 days, this is the equation, this quadratic equation. That's how the cases are modeled. Assuming the number of new cases begin to decline after day 11, what is the maximum number of new cases in one day? So after the cases become a quadratic equation, then it's going to start decreasing. That's the assumption. So what is the maximum number of new cases in one day? So I'll give you some time to figure this out. Alright, so the maximum number of cases is actually, the number of confirmed cases is simply just actually, it's just after 11 days, because if we have an exponential in it, it's going to increase indefinitely. So it's going to constantly increase and it's going to get faster and faster. It's going to be very steep. So we know that's when the cases are increasing. And we know that after 11 days it begins decreasing. Once it starts decreasing, then it can no longer be the highest number of daily confirmed cases, right? It makes sense. So the maximum number of daily confirmed cases has to occur after 11 days. It makes sense because that's when the growing of the cases stops. If you substitute 11 into the equation, 11 days, you should find that your value comes out to be 88.99, and that actually is about 89. So we'll say there's 89 new cases, maximum new cases in New Zealand on day 11. Maximum number of daily confirmed cases is 89. Question B, how long did it take for daily cases to reduce to 0? So once again, take some time and try to figure this question out for yourself. Alright, so for this question, you're actually looking at the second half of the equation, because that's when the cases start decreasing. With the exponential, cases are never 0. Okay, for the exponential, the cases are never ever 0. So you know that won't work. So you know that the number of cases can only become 0 in this quadratic when it starts decreasing. So when it starts decreasing from the maximum, eventually after some period of time, the number of new cases is going to drop down to 0. So looking at this equation, we need to solve for when the number of new daily confirmed cases is 0. So we're just solving a very easy quadratic. This is a very simple question. Plug into your graphics calculator. You'll get that t is 27.3 days. So your answer to this question would be about 27 days, or on the other hand, you could also say 28 days. It doesn't really matter. Both are valid answers. So 27 days or 28 days. Okay, so next question. So the daily new closed cases, so that's recoveries and deaths, closed cases, is modeled by r equals to 1.0331 e to the power of 0.4104 t minus 9. Okay, immediately looking at this graph, we have t minus 9 in the power. This means that the recoveries are generally lagging the cases by 9 days, because we're doing t minus 9, so it's actually being shifted 9 units to the left. From a graphical point of view, the graph has been shifted 9 units to the left. Okay, that means that everything's happening 9 days after, technically 9 days after what it should be happening. Okay, and that makes sense in the real life, because as soon as someone gets infected, it's going to take some time for them to start recovering, and that's how we get that t minus 9. That's generally the amount of time when people start recovering from the disease and illness, or on the grim side, people might start dying from the disease, so that would be our lag time for the recovery is lagging by 9 days. You can tell that immediately by the formula. Question, so it's valid for t is between 20 and 0, a very important restriction. When does the daily new closed cases first overtake confirmed cases? So I'll give you some time to find the answer to this question. Remember, for this question, you don't necessarily have to find, because if you try to solve the equation, it's actually very difficult. So on the other hand, you can actually try drawing up a table, and if you draw up a table, you can find one function and the values over time, and you can compare the two values. It might be a bit easier, because solving the equation is a bit difficult. You might have some hard time doing that. So I recommend you just draw up a table, and you have your recoveries and deaths on one side, and your new cases on another side, and your days on one column. There you can see the daily new cases and daily closed cases. Okay, so we know recoveries lag new cases by 9 days, so the overtake has to happen on the 11th day. So by the time we're confirming 89 cases, so let's say on day 11, we're confirming 89 new cases. That's the maximum number of cases. But however, because the recoveries are lagging the cases by 9 days, realistically it's only the second day for recovery, so it's going to be a very small number. So in that case, the number of new cases is going to be very, very much larger than the number of recoveries. So automatically, you know from this intuition, you just know that justification, that the recoveries are going to pass the new cases after the new cases start decreasing. So after it's getting modeled by the quadratic, it's going to start decreasing, and that's when the recoveries are exponentially increasing, and the new cases are following exponential decay a little bit, like not necessarily exponential decay. It's not that exact graph, but a quadratic roughly models that type of decay. So the question here is so if this is the answer, so this is what you would, if you wanted to solve the equation, this is the equation you would get. So our quadratic is less than so basically our new confirmed cases is less than our recoveries. However, this is a very difficult equation to solve because you have a quadratic within an exponential. So I think a better way to this question, we should probably use a table instead. So this table shows days on the left-hand column and new closed cases and new confirmed cases. So in order to draw up this table, you can just substitute days 11 into the formula. So t equals to 11, substitute t equals to 12, substitute everything, and then you'll find a pattern. For example, on day 11, we have 89 new cases and 2 new closed cases. On day 12, we have 85 confirmed cases and 4 new closed cases. On day 13, we have 74 new cases and 5 closed cases. As you can see here, number of cases is decreasing. Number of number of new cases are increasing. Number of cases are decreasing. Number of closed cases are increasing. So eventually, the number of closed cases are going to overtake number of cases. And if you notice, that actually happens on day 18. On day 18, we have 42 new closed cases and 31 new cases, and that's the first time when recoveries overtake cases. So your answer to that question would be, the number of new closed cases overtakes the number of new daily cases on day 18. Alright, so for the final question here, this is a very difficult question. We have an excellence level question coming up here. Maybe even scholarship level. I don't know how they do it these days. But last question, what is the maximum number of increase in active cases? An active case is defined as the daily new cases minus daily closed cases. Calculate this based on the assumption that both exponentials of closed cases and new cases are continuing indefinitely. This means that both exponentials will rise forever. So assuming that there are no boundaries on the time, so this means that the exponentials can rise forever, and non-ending exponential, okay? So this is, given that is based on this assumption, find the maximum number of active cases. And when I say maximum number of active cases, I mean the maximum number of daily confirmed cases minus daily closed cases, okay? That's what I want to find. So I'll give you some time to find an equation representing this active case count, and I'll try to solve this question. Okay, so this is a high level question here. Alright, so what I have here is active cases equals to current cases minus closed cases. So we have our current cases would obviously be our exponential, which was our c, and our closed cases, which would be our r. Okay, so it would be a equals to c minus r, and it will be the difference of these two exponentials. In order to find the maximum value of a function, so this in itself is a function now, we're trying to find the maximum value of this function. So now we need to make the derivative equal to 0. So first things first, we need to find the derivative. To find the derivative, we just need to find the derivative of the power. So the derivative of the power would just be taking the t away. So if you find the derivative, it's just according to the power rule. So derivative of 0.3974t, that becomes 0.3974. And now you do 0.3974 multiplied by 1.1243, because the power gets moved, the derivative of the power gets moved to the coefficient. It gets multiplied by the coefficient. Should be getting that dA over dt equals to this function here. And if we simplify this equation a little bit more, we'll get that it becomes this equation here. How did I get negative 3.6936? I expanded the brackets. I expanded the t minus 9. So negative 9 times 0.4104, that gives us negative 3.6936. Alright, so now a very key concept that I want to explain now is moving the negative 3.6936 to the coefficient. How are we going to do that? That seems really very complicated, very random, and very doesn't really make sense right now, right? Okay, so let's put it in a way that does make sense. Let's say we have an exponential. Let's say we have 2 to the power of x, right? Let's say we have 2 to the power of x plus 1. What does 2 to the power of x plus 1 really mean? Think about it. What does 2 to the power of x plus 1 really mean? 2 to the power of x plus 1 actually means that on the basis of 2 to the power of x, we're multiplying by x plus 1, which is multiplying by an extra 2. That plus 1 means we're multiplying by an extra 2 on top of the amount of x times we've multiplied 2. So for example, if we have 2 to the power of 3, if we have substitute x equals to 3, so we have 2 to the power of 3 plus 1. So we have 2 to the power of 3, which is 8, multiplied by an extra 2, which it becomes 16, becomes 2 to the power of 4. Likewise, if we have 2 to the power of x plus 1, we can use our indices rules that we used in our previous slides. We used the indices rule to split the equation. We can also say 2 to the power of x plus 1. We can say that is equal to 2 to the power of x times of 2 to the power of 1, because we have x plus 1. So therefore, we can say that that's equal to 2 times of 2 to the power of x. Alright, similarly, let's say it's minus now. Let's say it's now 2 to the power of x minus 1. A minus represents that we are now multiplying by 1 less 2 on the basis of x. So let's say we have a random number for x. Let's say we have x equals to 3. If we have x equals to 3 and 3 minus 1, that means we're multiplying by 1 less 2. And when we say multiplying by 1 less 2, that means we're technically dividing by 2 to the power of 1 in this case. If we have x minus 2, then we'll be dividing by 2 to the power of 2. Likewise, we can also use our indices rules here. Our indices rule states that if we have 2 to the power of x divided by 2 to the power of 1, if we divide two bases with if we divide two same bases with different powers, we can just subtract the powers. The same way we can split them up. So in this case, if we have x minus 2, we can split the x into minus 2. We can say that's 2 to the power of x divided by 2 to the power of 2. That becomes 1 over 4 times of 2 to the power of x. Alright, coming back to this question now, we have e to the power of negative 3.6936. If we take the negative 3.6936 out of that power, we'll simply just get this coefficient 0.4230 multiplied by 1 over e to the power of 3.6936. That's just following our indices rules and our logical rules here. So if we do that, then we'll get this new equation here. The reason we did that was because we wanted to eliminate all the non-t factors out of the powers. That makes it a lot easier for us to get rid of to simplify this equation. Okay. To further simplify this equation, we moved one function to the other side, and now we can separate the variables. So we can put the constants together and we can put the e's together. So like I said, back to our indices rules, if we have two same bases divided by each other, it's simply just the powers. We simply just subtract the powers, right? So for example, 2 to the power of 2 divided by 2 to the power of 1, that equals to 2 to the power of 2 minus 1, right? Same thing here. We can just subtract the powers, okay? If we subtract the powers, we'll get e to the power of 0.013t, and that's equal to some constant, okay? That's everything on the right hand side. Remember at the start, I was telling you how ln of x is basically telling us e to the power of what is x. Same thing here. If we move we can see this is moving e to the other side. We can also interpret this as if we have how we purpose this. Take it back to level 2. So in level 2, what do we do in level 2? Right, in level 2, for example, we have 2 to the power of x equals to, we have 2 to the power of x equals to 4, right? That's basically the same as taking log of both sides. So 2 to the power of x equals to 4. That becomes x log 2 equals to log 4, right? That's basically the same thing here. We're just taking the natural log of both sides. Because once again, natural log is just log base e. It's the same thing. So if we take log base e of both sides, we'll get ln of that constant is equal to 0.013t. If we rearrange for t, we'll get t equals to 222.15 days, and substituting back into our equation, and we'll get our answer. If we substitute this back into our active case formula, we'll get our final answer is 1.4517 times 10 to the power 38 active cases. This is actually impossible in real life scenario because cases and closed cases are not rising forever. In this calculation, we purely based on a calculation of mathematical maximum, which is a theoretical maximum. It will not happen in real life. There is not that many people, and there's not that many. It's just impossible because in reality, there's no exponential that rises forever. In real life, all exponentials will eventually flatten out or curve back in the opposite direction. So this is impossible. the actual true maximum occurs on day 11. The reason it occurs on day 11 is because our exponential was valid for the first 11 days. So our true maximum occurs on day 11 when the new cases are increasing and the recoveries were really slow at the start. So the number of daily reported cases exceeded closed cases by 86.65, or about 87 cases. After day 11, the announced new daily cases drop, while closed cases increase, meaning the difference between new cases and recoveries will begin to decrease, and eventually recoveries will exceed new cases. So once the closed cases increases and the recoveries, while the closed cases increase, but the confirmed cases decrease, the difference between them two decrease until eventually the number of recoveries and closed cases will exceed the new cases. Alright, so that's all I have for this presentation. I hope you enjoyed this presentation. In this video, I really hope that you understand more about E and ln on what they exactly are, instead of just blindly using formulas and just, e to the power of x derivative of e to the power of x is e to the power of x. Why? Because it is. Because hopefully this has allowed you to understand why is e to the power of x derivative is e to the power of x. A bit more background knowledge into your NCEA and your questions that might help you in the future to get a more broader understanding of mathematics. I hope you enjoyed this video. It took me quite a long time to make, so I really appreciate it if you could drop a like below and give me some positive feedback, and that would be great. And for now,